So welcome also from my side. I'm Sabine Österle. I'm the scientific project manager of the FI group, the Personalized Health Informatics group. And it's my great pleasure to introduce Jean-Louis Raisaro from SPHN. He will today present us about SPHN Semantic Strategy in action. So I think this is a very important step we did in actually in a collaborative work where all hospitals or university hospitals were present to do a first pilot in how we can use RDF as a data exchange format for SPHN. And again, I think I would like to take the opportunity here to thank the whole group which heavily worked on that. And I think we are very happy to hear all the insights in how this would work, what are the challenges, what do we need to consider when we take that path, and then also continue doing this work, because again, it's a pilot, it's the first step. It's still a long way to have that ready to be used just off the shelf for all projects, but I think we come there.
Okay, good morning, everybody, and thank you, Sabine, for the introduction and for having me here. So it's my pleasure to present you the work we did in the context of the task force related for the data exchange format in SPHN. So most of the slides I'm using here are were kindly provided to me also by Christian Levis and Catherine Kramery. So I thank them for this. So to well understand where we are coming from and where we want to go, just wanted to provide a little bit of introduction on the different working groups of SPHN in which I have the pleasure and the privilege to be part of. So as you know, DCC is playing a fundamental role in the SPHN initiative and try to coordinate the activities around the different driver projects and infrastructure development projects, but it's also leading two working groups that are responsible for defining and implementing the data semantic strategy of SPHN. So these two groups are the Clinical Semantic Interoperability Working Group, which is led by Christian Levis, professor in Geneva, and the Hospital IT Working Group, which is led by Cornelia Kruschel from University Hospital of Zurich. So to really understand the context, it's very important to understand what are the missions of these two groups and the mandates. So the first group is composed of, let's say, semantic experts from each university hospital, and has the goal to develop a semantic-driven framework that enables secondary use of medical data. And by secondary use of medical data, I don't mean only for research purposes, but also for regulatory agencies or pharma industries or healthcare. So the work of this group is basically definition of health-related concept and a strategy to use these concepts to represent medical knowledge that it's actually stored and used in healthcare within our hospitals. And the work of this group is in tight collaboration with representatives and of hospital data warehouse teams and scientists working in driver projects. On the other side, you have the Hospital IT Working Group, whose goal is to take what has been defined by this Clinical Semantic Working Group and try to implement and provide recommendation and guidelines on how to do this in a practical way. So the working group works as follows. So they set up like time-limited task forces that try to address one specific topic. The main topics currently are the federated query system that is provided by the company here in Basel, Kleinerion, the data exchange format, of which I'm going to talk about today, the de-identification, and data catalog. So each task force is meant to provide recommendation, bring in national or international experts, and then provide a series of deliverables in forms of documents that hospital can use to develop and implement the strategy. Voilà. So today I want to talk about the experience we had in the task force for the data exchange format. So very important to understand is that the landscape of clinical data is amazingly complex, which means that you have data from multiple sources collected for multiple purposes, that you use different ontology standards, different data models. But the main message of SPHN is that we want to be at the center of different communities, from the healthcare, the pharma and regulatory community, but also the research community. So there's not really one standard that fit all these communities and fit all our purposes, which means that we cannot pick one and just reuse it in SPHN. Also because every model and standard has its own strength and limitations, and you will understand in the following slides why this is the case. So the strategy we propose here, it's a three-pillar based strategy, where the first pillar, so I'm going to go through each pillar in more detail, but the first pillar aims at building a strong semantic framework that enables to achieve semantic interoperability between data that is coming from multiple sources, so multiple hospitals. The second pillar is about a description formalism that is able to describe this semantic and store data in such a way that it can be easily transported and transferred. And then the third pillar is the ability to convert this data to different data models depending on the needs. The needs you have to use this data. So it can be for research purposes, but also for quality purposes, for healthcare purposes, or for regulatory constraints. So the two groups that I talked to you about before are responsible for these two first pillars, and together with projects, they work in getting this data into the right format and data model that is suitable for SPHN driver projects. So to understand the second pillar, which was the goal of the task force, we need to understand the first before. So what it means, like building a strong semantic layers. It means that what we are trying to build in SPHN is something that is standard or ontology agnostic. So we don't want to depend on a single standard, but we want to be able to reuse existing standard when it's needed. Just to make you an example, when we want to achieve semantic interoperability for diseases, we are going to use, for example, ICD-10, so the International Coding Standard for Diseases from WHO. But when it comes, for example, for laboratories, we're not going to use ICD-10 because ICD-10 doesn't suit the purpose, but we're going to use LOINC. And for other things, we're going to use other standards, which means that what we need is a kind of generic framework that enables us to use the standards we need when we need it. So the goal, of course, is to serve the collaboration agreement of SPHN between the Swiss Academy of Medical Sciences and the university hospitals, but also the driver projects, the feasibility query tools, and so on and so forth. So in order to do that, what we developed in the Semantic Working Group is a compositional approach, where basically we try to represent medical knowledge with concepts. And concepts are independent of the concept of the context in which they are used, which means that you can define a concept as a sort of an atomic entity that can be afterwards reused to build more complex or so to say composed concepts that are like concepts more targeted to a specific use case or to a specific context. So you see here, it's like a Lego building block approach where we define very simple concepts and then we reuse those building blocks to create more complex concepts. And this basically allows us to extend the representation of medical knowledge in a very easy way, because anybody can come from driver project, define their own concepts, and then build up to represent what they actually need to represent, so that every hospital then can really understand what data has to be transferred. So just to give you an example, here is a composed concept that is named lab results. So this is meant to represent the result of a laboratory test, and it's composed by sub-concepts like the concepts code, which is a concept meant to represent a code coming from a medical classification, a terminology, or an ontology, for example, LOINC. And also it's composed by a concept of material, which means that what is the material used to get this lab test. And of course, concepts can take values in value sets, and it's at this point where we try to use existing standards. So value sets, we try to map internal value sets of hospital to existing standards, like, for example, LOINCs, which means that the lab results is using a concept of type code that can take any value in the LOINC ontology or terminology. Same for material. Here we use, for example, a value set taken from eHealth Swiss and the Federal Office of Statistics that is represented here as an example. So again, another example. So how do we build this kind of data set of concepts? We basically try to define those in this way, where we define the main concept, and then concepts are composed of different attributes that are meant to describe this concept, and then attributes that have a type, and type can be value set, or it can be the type of another concept. So you remember, concepts are used to compose other more complex concepts. And here you can see easily that body site, it's a kind of atomic concept that is used to compose more complex concepts like catheter or temperature. So here comes also the value set, so which means that the value set, we try to choose it when available from international standards, and when it's not available, we try to see what's available in hospitals, and we try to come up with a common value set that fits all hospital needs. So I hope you got the gist of this semantic approach. So what comes afterwards is, how do we get from there to the actual transfer of data? So everything seems really abstract to this point, but you'll see it gets very concrete in a little while. So there are several description formalism out there that are used to represent semantic. So the goal of a description formalism is to try to represent semantic in a way that we can express new things without losing information. And to provide plasticity, meaning that it doesn't matter what we describe at the semantic level, our description formalism should be able to represent this in a formal way. And this is not the case, for example, for a data model, which is what people are used to work with and to store data with. Because data models are rigid, they come with definitions on how you have to store your data in tables with specific columns, specific value sets, specific attributes, and they are designed for specific use case. So they're not generalizable. So you cannot just pick one data model and say it's going to work for all the driver projects in SPHN. And what we want to to have is something, of course, that can be used for storing and for transporting data. So here, just an example to explain you why a data model doesn't work. So I just took an example, the Clinarion data model. So Clinarion is the company providing the software to SPHN for the federated query capabilities. And the software comes with a data model where you can store information from your clinical data warehouse. And the thing, we try here on the left-hand side, the yellow, we have the semantic data set with all the concepts and attributes that we have defined in the semantic working group. And if you try to map this to the Clinarian data model, meaning if you try to store information represented under this semantic definitions into the Clinarian data model, you'll see that there's a lot of information loss. Everywhere where you have NA means that there's no place in Clinarian data model to store this information, which means that if we use the Clinarian data model for sending data around for driver projects, sooner or later a driver project will complain because the data that they need, it's not containing that data model. And extending data models becomes very tricky. So this is not to show the limitation of Clinarian. Clinarian has been designed for a specific purpose, which is the federated query tool, and for that it works very well. But it's not been designed for being a generic solution for data transfer. And this is the same for any other data model. So the description formalism we chose is RDF. RDF stands for Resource Descriptive Framework, which is a framework used to describe web semantic resources. So it has been around for almost 2 decades and is maintained by the W3C consortium, and is being used by the main industrial stakeholders, so the big 4, Google, Apple, Amazon, and Facebook. And it's used also in the biomedical field. So there are many EU or MII projects that are using RDF to represent and store their data. Also, the European Bioinformatics Institute, so the EBI, is currently using RDF. And closer to Switzerland, there's Swiss Bioprot maintained by SIB, which is all stored and represented in RDF. And in addition to that, so there's several communities using this formalism, and several tools, open source and commercial, that are available around there to facilitate use of RDF encoded or data. So for people that are not familiar with RDF, I just have produced a couple of slides just to give you the main idea behind RDF. So RDF represents information as a collection of triples, which means that information can be organized with the following elements: so a subject, a predicate, and an object, where things can, so concept can be combined and instantiated through this kind of relationship, where, for example, dog would represent the abstract concept of the class dog, and then Rex the dog is a particular instantiation of that class. So you can really see that by expanding this kind of principle, you can build like graph of knowledge, of information, where each entity can be a concept or an instantiation of a concept, and the relationship that is that exists between different entities is just represented by arrows. And in this way, basically, you can represent all your information in a sort of graph that can be very extensible, where the relationships between the different entities are implicitly and inherently embedded in the data themselves. So which means that you don't need an explicit data model made of table that have like relationships between them with primary and secondary keys, but all the relationships are inherently contained in the data when they are represented as a graph. And it's a very powerful tool. So how to go from SPHN concepts to RDF resources? So this was the main challenge of the task force. So here on the left, you have a simplified representation of the heart rate concept, which has, in this case, just 3 attributes. So you have a value, you have a measurement date time, so when this heart rate was measured, and you have a unit of measure, so in which unit was actually the heart rate measured. And this can be mapped to RDF in a very simple way, where heart rate is a concept that is a subclass of another general RDF concept. And then all the attributes are so-called RDF properties, where heart rate is linked to these properties through the following RDF domain predicate. And then the different properties can take a specific range. So for example, heart rate, so the value can take a value in the range of integer, unit can be expressed as a string, and measurement date time can be expressed as a date time. So by building this for every concept, you end up with a so-called RDF ontology, which is a formal representation of the SPHN list of concepts that the Semantic Working Group has defined. The nice thing about RDF is that once you have your knowledge representation, so your ontology representation, you can instantiate each node of your graph for a specific data point, which means that if you come at the hospital and in your data warehouse, you have a specific heart rate value that was measured at a specific date with a specific unit. This is nothing else than an instantiation of the heart rate RDF class for that particular event, which means that if you want to store data in RDF, you're going to take the RDF ontology, and then you're going to have as many instantiations as heart rate measurements you want to transfer for a given project or a given purpose, which means that your graph just grows organically. And of course, the heart rate concept will be linked to a patient concept, will be linked to an encounter concepts, and then you will have all the information that you need in the RDF graph. So how the graph is then actually stored? The graph, there are different formats for storing RDF. So there are turtle files, which is an example here, JSON files, XML files, so all type of formats developer are familiar with. But basically here in SPHN, we have tried with turtle files, but there's files that have like really this triplet representation where you always have the subject, in this case is the resource universal identifier, which is this CH108 and so on and so forth. This has to be unique for every instance of a given class. And then you have predicates that are basically representing the arrows. So SPHN A00033 heart rate value, which means that it's this specific attribute of the heart rate class, and then the value that the attribute takes. So the predicate, the object of that predicate. So in the end, what you get is a long text file that is formatted as such, where every block is basically one node in a graph, and every line is representing one arrow of the graph and the value that it takes, so the ending node. So you can think of your data being represented as such with a very long file that can be easily then merged and integrated with similar files coming from other hospitals, provided that they follow the same knowledge representation, so the RDF ontology. Okay, so I hope to have provided you with an idea of how RDF works. So the third pillar is, how do we get this into something useful for end users? So well, RDF turns out to be really flexible and really manageable. So there are a lot of tools. The one we're using in the pilot is SparkQL. SparkQL is a similar query language very similar to SQL. So you can query your graph with some SQL query, and then transform your data in tabular formats or whatever you need. And SparkQL is a very powerful tool because you can basically store your turtle files, so the files I showed you before, in a SparkQL endpoint or engine, and then just write simple SQL type queries to get to know your data. And what's very interesting about using RDF instead of a data model is that you just need to know the ontology to query your data. You don't need to know the data model underneath. You don't need to know the relationships underneath, which means that anybody can query the data in RDF, provided that they can understand the ontology. While for if data was stored in different data models, then you would need to know the structure of each data model in order to be able to query your data. So the idea is that we can use Sparkle to transform data and store it in specific data models depending on what is the community we're talking to. So for example, we can transform Sparkle in CDISC if we're talking to the pharma industry, to HL7 if we're talking to the healthcare sector, or to OMOP or I2B2 common data model if it's for the clinical research community. So the goal is really, the idea is really having something that is that provides plasticity in a way that we can transform it to anything we need depending on our interlocutor. Voila. So this looks all nice, but then we tried really to implement this in a pilot project, which started in the end of November. So we focused on the PSSS driver project, which is the personalized Swiss sepsis project. The idea was to focus on a small set of concepts and their corresponding sub-concepts. And then we met in Bern, so representatives from each hospital, so data engineers that were very familiar with the local data warehouse. We met for a hackathon, of a 2 days hackathon in Bern, where we tried to come up with solution on how to transform data from our internal data warehouse systems to this knowledge representation RDF files. Of course, the hackathon was not enough to come up with a unified and single solution, so we spent December, and each hospital developed their local solution, and then we were able to validate on fake data our solutions, and really produce data that was in the end interoperable across all the 5 hospitals on these concepts. So basically, the data delivery cycle was the following, where data coming from data warehouse is firstly organized in project-specific views or tables in our data warehouse systems. We have to note that the data warehouse is different for each hospital. Each hospital has its own solution with its own data model, and data engineers work in a different way depending on their skills and their local systems. And after proper de-identification, these tables are fed into what we call the RDF translator, which basically transforms data from a relational data model into a graph representation that then can be stored in RDF turtle files. So the main challenge was essentially developing and building scripts, so code that was able to do this translation. And this translation was taking input the data for a specific project and the RDF ontology. And then we had a quality check mechanism that was taking what are called the shackle rules. So shackle rules are like rules that are used to verify that your RDF has been generated in a correct way, so in compliance with the definitions you provide in the RDF ontology. So we were able to run these shackle rules with really minimal errors that were basically due to formatting issues. And in the end, we got a set of turtle files that were completely compatible and interoperable. So what were the deliverables of the task force? So of course, everything is still on a draft status, but basically we built an automatic generation of the RDF ontology from the semantic data set that I showed you before that is defined by the Semantic Working Group, which means that whenever new concepts will be added to the semantic data set, the RDF ontology will be generated on top of it automatically, which is very nice. And shackle rules will also be generated automatically. And then we have drafted technical specifications and user guide on where that explain in detail how the RDF ontology has been generated and how hospitals have to use the RDF ontology to encode their data into RDF. So all of this is available. If you are interested to go to the link and provide comments and feedback, it's very welcome. We also provided Sparkle scripts that are able to provide quality assurance, which means that we're able to run some sort of statistical queries directly on the RDF data in order to check the integrity of what we export from hospitals and what we have in the data warehouse. And we have also data export scripts to transform RDF in tabular formats that are suitable for machine learning analysis, for example. And we have also generated quite a lot of fake demo data for training purposes. So if anybody wants to play with the data, they can just ask me or somebody else of the task force that will provide you with this data to play with. So ideally, all this documentation will be soon made available through the official SPHN, as official SPHN documentations. Of course, this is recommendations, so hospital can or cannot follow them, but they are recommended to do it. And what remains to be done? So of course, what we have done so far was a pilot, but there's still a long path before we can really claim this is ready for production. First of all, the main problems we encountered is that you have really to understand well what's RDF and the specifications and follow really the specifications in order to ensure compatibility. RDF gives a lot of freedom. So if you don't follow rules, it's easy to get files from different sources that are not compatible. So this is really a requirement, hard requirement. And a very important aspect that's it's independent of RDF, but that will ensure the long-term success of SPHN is that like local value sets, so the value sets of the concept we have in our hospital have to be mapped to common value sets that can be international standards or SPHN defined value sets to ensure interoperability. So as long as we don't do this mapping to common standards, there's no interoperability or whatsoever. So of course, this is time consuming and tedious work and often requires expertise from the clinical domain. So we are working with researchers from driver projects to get a sort of prioritization of what are the concepts that they need first so that we can really focus on getting this mapping done as soon as possible. Of course, then all the code that was developed by hospital, it's at a very prototype level. So this has to be further improved to ensure robustness and minimize the effort of the data engineer at the hospital side to deal with RDF. So ideally, what we want to have is a sort of black box where we just provide the mapping between our local databases and the RDF SPHN ontology. And then this black box takes the data and produces the RDF files automatically, regardless of the project or of your internal data organization. Very soon, a workshop with RDF experts and researchers of driver projects will be organized, also to advertise a little bit more what are the tools that can be used to use these resources. And DCC will take over on the management of the common resources, so the RDF ontology for the semantic data set, the shackle rules, and everything else that it's important to centralize so that each hospital can refer to it whenever they need to transfer the data. So this is my last slide. So to conclude, I hope to have convinced you that achieving sustainable semantic interoperability at national level is hard because medical data is extremely complex, but it's feasible. So we shouldn't give up. So, and what we propose is a three-pillar based strategy that ensures flexibility, extensibility, and reusability of health data. Most importantly, because we don't rely on a single ontology or a single standard, but we try to build a general framework that will use a given standard when it's really useful and needed. And the success of the implementation as the whole SPHN depends on collaboration between people with different expertise and coming from different domains. But I think this pilot was really an example on how this can be achieved if we really try to collaborate. And I think we're on a good path. So I hope to see more of this data in RDF coming for driver projects in the next few months. Thank you for listening.
Thank you very much, Jean-Louis, for a very clear, very interesting presentation for a very complex subject. Because I would like to open the floor here in the auditorium if someone has a question, Jean-Louis, or for those online, if you want to type them out, I'll read them out if there's any. Here in the auditorium, we have one back.
Yeah, thanks for the presentation, very clear indeed. I have a question about the metadata which is associated to the data. For instance, I'm thinking about the provenance. When we have ICD codes coming from a hospital, it might be interesting to know if it's come from the people in the billing department or if it's a code which was actually already put at the point of care. So I think, do you have a plan for this kind of metadata?
Yeah, of course. So the nice thing, thanks for the question. First of all, it's a very important one. So the good things of RDF is that can be easily extended, right? So right now in the pilot, we just focus on transferring data, but of course you can think about extending not the semantic definitions of the data, but the SPHN RDF ontology to also incorporate attributes that store metadata like provenance, and this is actually something we are currently experiencing with the PSSS project, for example, where for ICD-10 code in particular, we want to know if this is coming from the billing or from it was assigned during the encounter from a physician or a nurse, or for example from when you have the case where the mapping between your local value sets and the SPHN value sets is not a one-to-one mapping. So you want also to provide your local metadata, let's say your local value sets to the researcher so that they can really understand how the mapping was performed, something of this kind. And RDF is really flexible because it allows you to basically extend really the ontology as you need. So the goal is really to try to do this in the best and a collaborative way so that not every hospital or every project does its own way, but it's kind of centralized and orchestrated by the DCC.
Yeah, there's more questions.
So this is a huge endeavor, and you go into production, and is there any indication what is the timeline or what are the plans with regard to the time?
Yeah, so this is kind of attached to the funding provided by SPHN. So right now there's funding until the end of 2020. So by contract, hospitals have to be into production by the end of 2020. So able to generate RDF an industrial way to transfer data for driver projects. So this is the expected timeline.
Maybe a bit provocative question. You said that the shackle rules are somehow the quality control step. Are they sufficient? Because, yeah.
No, so shackle rules are good to check if RDF was generated in the right way, so the format, but they don't check on what's the data stored by RDF. So which means that you always need to do some consistency check between what you have locally in the hospital and what eventually you're going to export. This is why we implemented some Sparkle queries in addition to the shackled rules to verify that the distributions of all the concepts was essentially the same before the encoding into RDF and after.
So you really say that we need to work on how are we doing, especially now in the beginning, a quality control step that we really achieve the interoperability.
Yes, yeah.
Another question here in the auditorium.
Is the production of the RDF files, so now you did it for the sepsis study. Is the idea that for a specific study, RDF files are produced from a hospital and delivered to the study, or are the RDF files in general? This is the first question. The second question is, what are the priorities? So I can imagine that for laboratory, it's quite feasible because standards are well established, and maybe also for radiology also. How is it for other fields like clinical data, like also microbiology data, for example?
Okay, so to answer your first question, so right now our strategy is to generate RDF on a project basis, which means that every time there is a new project coming, they come with a list of concepts they want to obtain, and then the hospital, they do a sort of mapping between this list of concepts and their internal data warehouse, and then this RDF engine basically generates files for the specific project, and then they are securely transferred to the project researchers. And to answer your second question, so there's currently a priority in all the projects. So first, we are targeting concepts that are of broad interest, so that are reused by several projects. And these are concepts more related to, as you were mentioning, laboratories, medications, diagnosis. So the ones that are easily retrievable from the billing process, where the data is already encoded. And then we're going to move slowly towards more specific variables. So microbiology is one of those. Genomic data, we're working on this. But of course, it's a kind of a continuum where we try first to satisfy, let's say, 80% of the use cases by providing these core concepts. And then we try to extend this list with more specific concepts, where more often than ever, there's no really standard existing. So we have to come up with experts and try to see what's the best way to semantically represent this information.
Yeah, I think so. All this implementation in the local hospitals actually need to rely on local efforts. So how do you check that when a new concept comes in the ontology that every hospital is implementing it, or more like which tools are you developing to help the hospitals verify how compliant they are with the national standards? Yeah,
so we're currently like exploring two paths. Essentially, one path would be to build a centralized solution to generate this RDF that it's kind of independent from your internal infrastructure. And then like data engineers works in a way that generate the input data in such a way that it's compatible with this single unified solution. And this will basically guarantee that all the output data is the same for each hospital. Nevertheless, there's this also second option where hospitals, which is what we're currently doing right now, is hospitals implement their own solution because systems are so heterogeneous among each other, which is very difficult to come up with a central unified solution. And then we are actually trying to figure out how to provide the best quality measurements and assessment to make sure that solutions are generic enough to work whenever a new concept works, because of course in software development, devil is in the details. So whenever you believe you have a generic solution that works, it comes to the new variable with a kind of corner case and everything breaks. So it's challenging. It's challenging, and we have seen this in the pilot where hospitals have more or less tried to build a generic solution, but none of us has really achieved. So we'll see if we can move towards this path or not, or maybe try to the central one. So this is still in work in progress, but we're exploring the two ways. Yeah.
So I think with this, we come to a conclusion. Thank you very much, Jean-Louis.
Thanks to you
for
for having me.
Thank you very much for attending. See you next time.